Okay, so Unit 5, which is what we're going to start today, and will take us mostly up until winter break, is about electrons and energy, and we're going to talk a little bit about that today and some really basic stuff. One of the things we're going to talk about today is something called electromagnetic radiation. Also, it is sometimes abbreviated EMR, because electromagnetic and then the radiation part. Okay. But what you should know is that electromagnetic radiation is not actually matter. It is simply energy. And it's energy in the form of waves. And the light, the visible spectrum, the light that you're able to see, is a small part of the electromagnetic spectrum. And we'll talk in greater detail about the actual electromagnetic spectrum tomorrow. But light tends to behave like a wave. And when we think about waves, we often think about waves on the water that look something like that. Okay. But light itself is energy that behaves like a wave. So the light that's coming out of the light bulbs up above us, or the light bulbs in the headlights of your car, basically that energy that is coming at you that your body interprets is a form of a wave. Now, light, when it acts like a wave, it can do a couple of things. One of the things it can do is it can exhibit something that we call diffraction. Which is this right here. Diffraction is when light, which is a bunch of actual technical different colors or energies, enters into an object that bends the light itself. So when the light comes into the object, like a prism, for example, the light itself changes its path and it bends. And then when it does that, it diffracts, or it separates into the different colors of light itself that make up the light that we're starting with. So, and then when it leaves the prism, it spreads out even more and it's easier for us to see. So when you see a rainbow, like out in nature, right, the raindrops in the sky are actually behaving like tiny prisms. So the light from, like, say, the sun is traveling through the sky, and it enters into a raindrop, and when it leaves the raindrop, the white light that we see gets bent into the shades of color that make it the rainbow that we see. Okay, because we got your reds, your oranges, your yellows, your greens, blues, indigos, and violets. Remember that from when you were a little kid? Okay, now the next thing that light can do is it can exhibit the property, well, not the property, but it can exhibit refraction. And refraction is when light goes from one state of matter to another state of matter, it changes speeds. So when light is traveling through a gas, like air, the air particles are super spread out, and the light itself doesn't have a lot of things to run into, so it travels at a very consistent speed. But if light were to travel into, say, water, which is a liquid, right, that liquid is a little bit more dense, meaning that the particles are closer together, and as a result of that, the light ends up slowing down. So as the light travels from air into a thicker medium like water, the light wave itself, or the light beam of energy, slows down. And when it slows down, what happens is that it bends as well. So we oftentimes see this image where you have like a straw in a glass of water, and the straw looks like it's kind of like broken. It's not actually broken, as you are aware from your personal experience, but it is simply but the light waves have slowed down when they're in the water, and it appears to be this illusion that the straw itself is broken. That's what we call refraction. Another type of thing of property of electromagnetic radiation is something we call interference. And that's an example up here. So when light has, or beams of energy or waves of energy have similar amounts of energy, and they come into contact with one another, they can do one of two things. They can either become stronger, or they can cancel each other out, and that's what we call interference. So if you're looking at this picture of the stage and the lighting from the stage, what ends up happening is that as two beams of light cross each other, you can see that that where they cross appears to get brighter. And the reason why it appears to get brighter is because both of those waves have similar energy, and when those waves come into contact with one another, the waves themselves grow and get bigger. And when they get bigger, they produce a stronger light. Now, the opposite can be true as well. So if you have a wave, and this is sort of how noise-canceling headphones work, like an oversimplified version. The noise-canceling headphones, the program or the computer chip inside the noise-canceling headphones detects the rate at which outside energy waves or sound waves are coming in, and they essentially produce a frequency that is the opposite of it. So they basically make another wave come into contact with the wave, and the peak and the trough are off, and they cancel each other out. So that's kind of what happens with noise-canceling headphones. The noise-canceling headphones use frequency to cancel out the energy that's coming in, and as a result, you don't hear anything other than the music that you're listening to. So that's kind of like what interference is. And I guess the best way to look at it would be if I had a wave that was like this high come into contact with a wave that was this high, and they were like in the same frequency, or they were in the same rhythm, the wave peak would get bigger. But if the waves were opposite, where like this part and this part meet, the wave would cancel itself out. And that's what interference is. And I did not do a good job of drawing that, but that's the best that I can do for today. So there are some other properties of waves that you're going to be responsible for understanding, and one of them is something that we call the wavelength. The wavelength is the distance between two corresponding points on a singular wave. So in this drawing right here, if we measured the wave from that spot to that spot, first of all, this part right here is all considered one singular wave, right? And as a result of that, the distance from the beginning of the wave to the end of the wave is something that we call the wavelength. But we can measure them at different spots. So if I measured from top of wave to top of wave, that would also be a wavelength. And I can also measure it from like bottom of wave to bottom of wave. So that would also be a wavelength. Wavelength, though, is a length measurement. And it's measured either in the meter or something called the nanometer. Okay. Now, the bigger the wavelength, the bigger the unit we're going to use to measure it. So if a wavelength, if a peak of a wave to a peak of a wave is really far apart, we'll use meters. If the peak of the wave and the peak of the wave are really, really close together, we will use nanometers. Okay. So that's one property of waves. Another property of wave is something that we call the frequency. Okay. And frequency is simply defined as the number of cycles of a wave that pass by a given point in 1 second. So if you're sitting, like, for example, on the beach and you're counting waves come in and hit the beach, right? that would be a measure of the frequency of waves in terms of water. Well, energy waves have the same thing. So basically, we are looking at a given point. So here's my given point, right? And we're going to count the number of waves that pass by in one particular second. And so I have a better drawing here that you might be able to see. So in this instance here, what you could potentially see is that as the red wave passes by this point, I'm going to make an arbitrary guess, and I'm going to say that it goes by in 1 second. So peak to peak, it takes 1 second of time. Okay, but in the bottom wave, it looks like 2 or 3 peaks pass in roughly 1 second time. Does that make a little bit of sense? So that's what frequency actually is. However, frequency is measured in something that we call the per second. And I'm going to show you that in a second here. So frequency is measured in the per second. Now, we've heard the phrase per second before, like when we talk about, like, for example, speed or rate. It might be measure something like that goes an X number of meters per second. Well, we're talking about per second. We're really talking about second, like -1, if we're going to talk about it in math way, or 1 over second is the frequency, essentially. So in this instance here, what we end up having is we have these waves, right? And the top one has a long wavelength. And so as a result of it, that it has a low frequency. Whereas the bottom wave has a short wavelength. And as a result of that, it would have a high frequency. So the shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. And then the last thing that we're going to talk about today is the energy of the wave itself. So energy is the relationship between wavelength and frequency. And what that means is that if I'm going to compare two different waves, like in this case, I'm going to be comparing the relationship between how big the wavelength is and the frequency of one wave to another, and I could identify, or I can make comparison in terms of the amount of energy present. So here in the first one, I can say that I have long wavelength, right? And so as a result of that, I would say long wavelength. And I can predict that because the wavelength is really, really long, that means I'm going to have a low frequency. And so what that really tells me is this wave would be considered to have low energy. So the longer the wavelength, the lower the energy, the lower the frequency, the lower the energy. Now, in the bottom wave, comparatively, I have a short wavelength. I can predict then that I have a high frequency. And as a result of that, I'm going to have higher, or in this case, high energy. So what this means is that the closer the waves are together, the more energy they're going to have. The longer the waves are apart, the less energy they're going to have. Okay? And that's really what we're going to cover today. Any questions about the properties of waves as we talked about in class right now? Wonderful.